In these last two exercises of this section, we are going to see groups of order PQ, where P and Q are prime numbers. So here in this ninth one, we have one such group G whose order is PQ, where P and Q are distinct prime numbers. And additionally, it is given that G has subgroups of order P and Q, both of which are normal. We have to then prove that the group G is in fact a cyclic group. So let us see the solution. We will of course start by assuming such subgroups that are given to us. Let H, K be not just any subgroups, but okay, we can continue like this: B subgroups of G of orders P, Q respectively such that both H and K are normal in G. Actually, I should have written the word normal here itself. Let H and K be normal subgroups of G of orders P and Q respectively, but anyway, it means the same thing. Note that H and K are both groups of prime order, and we have already seen in one of the previous exercises that such groups are cyclic groups. Since H and K have prime orders, they are cyclic groups. I don't think this is coming from an exercise, but it is the last result on that section where we have Lagranges theorem. I think that's where it is coming from, but it is something we know. So that means these each of these two groups will have its generator. Let H be generated by the element H and K be generated by the element K, where H and K are some elements in our original group G. Now we look at the orders P and Q. Because P and Q are distinct primes, they are relatively prime. That means their greatest common divisor is 1. So because of this, Lagranges theorem implies that H and K would intersect trivially. Why though? See, H and K, their intersection is a subgroup of H. So by Lagrange's theorem, the order of this intersection should divide the order of H, but the order of H is P. So that means the order of this intersection can either be P or 1. But if it is equal to P, say if this is equal to P, then these two sets would be equal. Why? Because H already has P elements. Now if this subset also has P elements, the only possibility is this. But this then would in turn imply that H is a subset of K and hence a subgroup of K, because both are subgroups of G. But then again Lagrange's theorem implies that the order of H should divide the order of K, that is P should divide Q. This of course is not possible because P and Q are relatively prime. So that is why order of this intersection cannot be P. So the only other possibility is that it has to be equal to 1, and that is why the intersection is trivial. It looks like there are many steps in between, but those steps are very easy and common steps that we always encounter and keep encountering in group theoretic arguments. So there is no need to show them, okay, with that much detail. Hence, the order of Hk, if one considers this product of the subgroups, is by a previous result order of H times order of K divided by order of H intersection K. This is P, this is Q, this is 1. So that means you get PQ, which is equal to order of the entire group. But Hk itself is a subset of G by the closure property. Thus, we get G equal to Hk, because Hk is a subset of G and they have the same number of elements. Both are finite, of course. Okay. So this is one thing, we are going to use it, but now we haven't used the normality part of the hypothesis. We have just used the fact that the orders of these subgroups, each one of them is a prime number. So we used the fact that they are cyclic and we have done some things like this. Now we are going to use the fact that H and K are given to be normal in G. Since H, K are normal in G, we have, shall I write it here? Okay, let me write it here in the middle, it will be more prominent. Hk, H inverse, K inverse belongs to the intersection of H and K, which is of course the trivial group, and hence Hk, H inverse, K inverse is equal to E, or Hk is equal to Kh. Okay, normality of H and K, we are saying, implies this. How? You see that you can view this product like this. H, K, H inverse and then K inverse. Because H is after all a group element and K being the generator of the subgroup capital K is in K and capital K is normal in G. So this HK, H inverse, this element is in K. Take its product with K inverse, another element in K, this entire thing is in K. Okay, so using normality of K, we have been able to conclude that this belongs to K. Now do the similar thing slightly differently and consider this. H is coming from H, so H inverse also is in H because capital H is a subgroup, and then use the fact that capital H is normal in G. So K H inverse, K inverse, this is the conjugate of capital, this is the conjugate of H inverse, that would belong to capital H, and small h already is in capital H, so this entire product belongs to also capital H. Besides belonging to K, it also belongs to capital H, and that is why it belongs to their intersection, which we have shown is trivial. So that means this element has only one, this is the only possibility. From this, it follows that Hk is equal to Kh. Hence, G is abelian. Now, how am I making this conclusion? In the last line, you see that thing comes from this equation. G is equal to Hk. So, you take any element of G, it will look like this. H1, K1, right, and you take another element H2, K2, take their product and you can switch the order, you will get the same thing. But how is that following from these things? You see, every K, the elements of capital H and the elements of capital K all commute with one another. That's what we are seeing here. And how is that, where is that coming from? See, these are not just any H and K coming from capital H, they are actually generators. However, any other elements that this H1 and H2 coming from capital H are some integral powers of this generator, small h, like that K1 and K2 are some integral powers of this generator, small k. So because the generators commute, their integral powers will also naturally commute, which shows that all the elements of H commute with all the elements of K. So this K1 H2 you can write as H2 K1. And that H1, H2 will belong to H, K1, K2 will belong to K because they individually they are subgroups. Okay, so no, okay, that's not what I want to show. I want to switch the order. So after switching the order once in the middle, I get this, H2, K1, K2. Next, what I do, in place of H1, H2, I write H2, H1. In place of K1, K2, I write K2, K1. How am I going to do that? What is the justification? That is because I am able to do that because H and K are cyclic groups and hence they themselves are abelian. So that is why we can write H2, H1, K2, K1. And in this way, using the fact that the elements in H commute among themselves, the elements in K commute among themselves, and every element of H commutes with every element of K, and this equation you can clearly see, I mean you can complete this calculation and show that you can switch the order keeping the element the same. So that is why G is abelian. But we have to prove that G is in fact cyclic. That will now come. For that we need to produce a generator of the group, and our generator will be the product of the generators of the groups, subgroups H and K. That means small h, small k is our claimed generator. We now claim that the order of Hk is Pq. If we are able to show this, then we have got an element whose order is equal to the order of the group, so that will be the generator. Since the order of Hk is not equal to 1, it's enough to rule out the possibilities order of Hk equal to P and order of Hk equal to Q. See, because the group has order Pq by a corollary to Lagrange's theorem, I think the first corollary, if I remember correctly, the order of Hk can be one of these four values: 1, P, Q, Pq. We are already saying that it cannot be 1. Why? In every group there is precisely one element whose order is 1, which is the identity. Now in that case we have order 1, so if order of Hk is 1, then Hk has to be the identity, but then H is equal to K inverse, and we know that an element and its order have the what the hell am I saying? An element and its inverse have the same order. So according to that, the order of H we already know is P. Now since the order of K is Q, so order of K inverse is also Q. So you get the contradictory statement that P is equal to Q, which is false because it's given that P and Q are distinct primes. So that is why Hk cannot be equal to the identity, and so its order cannot be 1. So now if we can rule out these two possibilities, then the only possibility would be this, and we will be done. So that's what now we are going to do. Suppose that order of Hk is equal to P. Now we will reap the benefit of showing that G is abelian. Since G is abelian, we have order of this element is P means what? Among the other things, it means that the pth power of Hk is identity. So identity is equal to the pth power of Hk. Now because G is abelian, this is equal to this This is something I think we already proved way back in one of the exercises towards the beginning of group theory. And it's not just true for positive integers p or any integer p, it is true if the group is abelian. Anyway, now because capital H has order p and small h is an element of capital H, so this first power h to the power p becomes identity. So we get k to the power p. Also, because k is after all the generator of capital K whose order is q, so k to the power q is also identity. Now, since p and q are relatively prime, there exist integers, say alpha and beta, such that p alpha plus q beta is equal to 1. Then it's not b, it's k. K can be written as k to the power 1 by the definition of integral powers of group elements, and in place of 1 you can write p alpha plus q beta. Now use the rules of exponents available in the group. Using that, we can write this entire power as this: k to the power q or to the power beta. Now k to the power p is identity, k to the power q is also identity, so this is equal to identity, and this is a contradiction. Because if k is the identity, then it will generate a group of order 1, whereas it's given that the group capital K, the subgroup K generated by small k, has order q. That is the contradiction. We won't write those things, it's understood. A contradiction is similar contradiction arises from this condition, that order of hk is q. Hence the result. So that means our element hk must have order pq. So hk is a single generator of the whole group. It generates G. Now before I start exercise 10, I need a little ink. It's an asterisk one, that means it's supposed to be difficult. It has 4 parts, but before that we are given a group. Let G be a group whose order is again PQ, where it's given that P and Q are of course distinct primes, but this time it's given that P is the larger one. R primes prove A. G has a subgroup of order P and a subgroup of order Q. That is part A. Part B, if Q does not divide P minus 1, then G is cyclic. Part C, given two primes P and Q, such that this time Q divides P minus 1. There exists a non-abelian group of order PQ. And there is one more. Any two non-abelian groups of order PQ are isomorphic. So that's the thing. So this last one says that up to isomorphism there is a unique non-abelian group of order PQ. So let's now see the solution. For the first part, we are going to use a result that we have not got yet, but maybe there is a solution which does not involve using this advanced result prematurely. Like always, if you come across some such solution which uses only the things that we have developed so far in group theory, in any of these parts, then please let me know. I am going to use an advanced result. By theorem 2.11.3, G has elements of orders P and Q. These elements generate cyclic subgroups of orders P and Q. This theorem is the Cauchy's theorem. We have already proved Cauchy's theorem for abelian groups, but this is the general Cauchy's theorem which is true for any finite group. It just says that statement is the same thing, only now the group is not necessarily abelian. G is a finite group whose order is divisible by a prime number P. If this happens, then there is an element A different from the identity in G such that the pth power of A is identity. These two things, when you combine these two things, it follows that the order of A is equal to P. So that's what we have written here. Due to this theorem, and because P and Q, our P and Q divide the order of G, that is because G is of that order PQ. So we will find elements, one element of order P, another element of order Q. The cyclic subgroups they generate will be subgroups of order P and order Q. So that is the first one, part A. Then part B. Instead of using Cauchy's theorem, one can in fact go much further, even further away from where we are right now, a more advanced result, directly Silas theorem for finite groups, which would immediately tell you that G has subgroups of orders P and Q. That's just it. However, we haven't decided to go that far. But at the same time, in this part B, I think we are going to use a part of Silas theorem. So it's up to you. If you want, you can use Cauchy's theorem, and in these two steps you can get the required subgroups, or you can directly use Silas theorem, since we are anyhow using advanced results prematurely without proof. You can do that also, it's up to you. In B, it's given that the prime Q does not divide P minus 1. Then we have to prove that G is cyclic. Okay. Let H and K be subgroups of G of orders P and Q respectively. They exist by part A. So we have now concretely considered, we have given them names, P and Q respectively. And these subgroups of course are just like before, since their orders are primes, they are cyclic. Since P, Q are primes, these are cyclic. They will have generators. Let H be equal to this and K be the cyclic subgroup generated by K, where H and K are coming from our original group G. Now note that G has order PQ and P is greater than Q. Do you recall one discussion from a previous section where we said that if a group has this type of order and we have a larger one, a larger prime, and if there exists a subgroup H of order P, then that subgroup is going to be normal. And not just that, it will be, well, there we did not, we did not at once get the fact that H is normal. Rather, we showed that if there is a subgroup H of order P, then that is unique. That means if this type of groups have a subgroup of order P, where P is the larger prime, then that subgroup is unique. There is only one subgroup of order P. Back then we said that we would show that actually there is one such subgroup. So here we have shown that there is at least one subgroup of order P. There we proved uniqueness, here we also have existence. So that uniqueness we are now going to use. And the reference is this. We know that H is the only subgroup of G of order P, and it's coming from this. See the end of section 2.5. And because H is the only subgroup of G of a specified order, H must be normal. And this fact is coming from one exercise. And hence, H is normal in G. And the result that we are using here is this, exercise 9. Of section 2.6. So that means one of the subgroups H and K, H, we have proved that it's normal. and it's in fact a unique subgroup of order P. And there is one other fact also. Any element of G of order P belongs to H. Why? If that is not the case, if there is an element G not in capital H has order P, then the cyclic subgroup generated by G has order P, and the cyclic subgroup is not equal to H, and this would contradict the uniqueness of H as the only subgroup of order P. And why is this? Why are these two things different? That's because this cyclic subgroup naturally contains the element G, but G is not here. In fact, that's how we have chosen G. Yeah. So uniqueness of H would be violated. So no element of order P can lie outside H. All of them, if you encounter any such element in the group, that must, you will find that it must lie in H. Okay. Now our aim is to show that the other subgroup K is just like H, K is also normal in G. Suppose K is not normal. Suppose K is not normal in G. Now what you do, you think of the normalizer of K. The normalizer of K, let me just write one thing and then I will say why that is so. Since Q is prime, the normalizer of any subgroup you recall, for example here, is the set of those elements in the group for which this is true. That is, the normal subgroup condition is true. For those elements for which this is true, they together give you the normalizer. That means those elements which normalize K. We have already seen in one previous exercise that this is itself a subgroup of G, and not just that, it contains K inside of it. So that means if we are considering the normalizer of K, that contains K here, but K has order Q, which is a prime. So because K now due to this inclusion is a subgroup of the normalizer, so Q should divide the order of the normalizer, but the order of the normalizer itself should also divide the order of the group, because it is after all a subgroup of G. So Q should divide the order of the normalizer, and this thing should divide the order of G, which is PQ. So looking at these two divisibility relations, you can see that this order of the normalizer is either Q or PQ, but the order cannot be equal to PQ. Why? Because if the order of the normalizer is the same as the order of the group, then the normalizer would become, why am I writing H again and again? Then the normalizer, if this is equal to this, the normalizer would become G. But then every element of G would normalize K, implying that K is normal in G, contradicting our supposition. So that is why this cannot be equal to PQ. So the only possibility is that this has to be equal to Q, and that is why n of K is equal to K. Okay, the normalizer is the subgroup itself. Okay, now we are going to use results from Stiller's theorem, which will come towards the end of group theory in this book. However, let us also familiarize ourselves a little with Stiller's theorem. Let me first write the things down and then I will explain. Let S be the number of Q-Siller subgroups of G. Then by these two results, Q-Siller subgroups of G means what? Suddenly we are using something about which we don't know. For this, see section 12. Then by theorem 212.3 and lemma 212.6, P is equal to S is equal to 1 plus say PQ, where T is some integer. Okay, this far we have understood. Now what are these things? You see, say you have a finite group. Let us take a concrete example. S3, the symmetric group of degree 3. Now we know what its elements are. The identity, that function phi, psi, phi psi, psi square and phi psi square. Now we know that the order of S3 is 6. which is 2 times 3. What Silas theorem, in fact we have seen Silas theorem no? For abelian groups we have seen. You consider a prime number and you locate the highest power of the prime dividing the order of the group. For example, if you consider the prime 3, then the highest power of 3 dividing the order of S3 is 3 itself. So the Silas theorem says that there will be a subgroup of order 3. That's just it, that is the theorem, or that is rather the first half of the theorem. And we know that this group has a subgroup of order 3, which is the cyclic subgroup generated by psi. But if we choose 2, then again Silas theorem says that there is a subgroup of order 2. In fact, there are 3 distinct subgroups of order 2. That is fine, but Silas theorem says at least there is one. Now the second part of Silas theorem, oh, and by the way, this subgroup, for example, is called a 3-Silo subgroup. Because it corresponds to the prime 3. Any other subgroup, for example this one, this is also a subgroup, it's of order 2. It is called a 2-Silo subgroup. That's what we have written here. Let S be the number of q-Silo subgroups. Now see, here I am saying that there are 3 distinct 2-Silo subgroups. So for them the S is 3. So that is our S. S is the total number of q-Silo subgroups of G. Silas theorem first part guarantees that there is at least one, but there may be more. And the second part of Silas theorem says that there is a relationship between this. Any 2 q-Silo subgroups, they are conjugate, but that's not important for us. There is a third part of Silas theorem. Besides saying that that Silo subgroups exist, Silas theorem says that this number S of q-Silo subgroups has a special form in terms of Q. It looks like this: 1 plus tq, where t is some integer. If you look at a finite group whose order is divisible by the prime q, and if you manage to find out all the q-Silo subgroups, or rather how many q-Silo subgroups are there, you will see that that number is always of this form, 1 plus tq for some integer t. So that thing is one of these results. I think it is theorem 212.3 or lemma 212.6. I am not sure which one is which, but one of these 2 results says that the number is of this form. And there is another result which also says that the number can be given slightly differently. That other result says this: say G is a finite group whose order is divisible by a prime q, usual hypothesis, then the number of q-Silo subgroups, which we are denoting by S, is the index of the normalizer of, say, Q, where Q is a q-Silo subgroup. This number S is of this form, fine, but this is something else. If you manage to find one Q-zilla subgroup and find its normalizer, then you find the index of the normalizer. Divide the order of the group by the order of the normalizer, you get the index of the normalizer. That index would also be equal to the number of Q-zilla subgroups. Now for us, a Q-zilla subgroup is K in our case. So its normalizer we have seen, it equals K. Everything is coming from a supposition, but right now the normalizer is equal to K. So for that, what will be this index? Order of G is of course PQ, and this is nothing but K. Order of K is Q, so this is equal to P, and that is why we have written P is equal to S. Okay, so we have used many things which we have not got yet, and it will take some time for us to reach those places, but at least we understand what results are there and how we have used it. Proofs, of course, we will see later, but now let us see what we have got. We have in fact arrived at a contradiction, because looking at P and 1 plus TQ, what do you see? You see that P minus 1 is a multiple of Q, so that means Q divides P minus 1. But then Q divides P minus 1, which is a contradiction to the hypothesis which says that Q does not divide P minus 1. That type of Q and P only we are considering. So our supposition is wrong. What was our supposition? Namely that the subgroup K is not normal. That is, K must be normal in G. The result now follows from the previous exercise. What does the previous exercise say? In the previous exercise we had a group just like this one, a group of order PQ, where P and Q are distinct primes, and the group has normal subgroups of orders P and Q. We have to prove that the group is cyclic. Here also our group has order PQ, where P and Q are distinct primes, and in fact additionally it's given that P is the larger one. Now we have been able to show that there are subgroups of orders P and Q. Note the difference between this one and the previous one. In the previous one it was given that there are normal subgroups of order P and Q. Here we are only given the order P and Q. In part A we showed that there are subgroups of order P and Q. Now here we have shown that those subgroups are actually normal. So we are in a position to use the previous exercise result and that would tell us that the group is cyclic. That's what we wanted to show here. Then part C. In part C, what we have, here also we have two distinct primes P and Q, but this time Q divides P minus 1. If that is the case, we have to show that there is a non-abelian group of order PQ. We have to prove its existence. So we start like this. Let C be a cyclic group of order P, which of course we can consider, because cyclic groups can be constructed abstractly. In the examples we already encountered cyclic group of order n. Symbols of the form A0, A suffix 1, etc. to AN minus 1 and a binary operation. So one can consider a cyclic group of any order. And we have in the text determined the automorphism group of this cyclic group from example 281. From example 281 we know that the automorphism group of this cyclic group C is isomorphic to UP, where you know what UP is. UP consists of those congruence classes modulo P which are non-negative, and where the non-negative means, okay, I should not say non-negative, but those congruence classes modulo P which are non-zero and where the representatives are all relatively prime to P under multiplication modulo P. We have shown in this example that the automorphism group of any cyclic group of order P is in fact this. Isomorphic to this means group theoretically they are the same thing. Now since UP is itself abelian, its order, we know the order of UP, P minus 1. If you had a UN where n is any positive integer, the order would be the Euler phi function value of n, phi of n. Phi of P is also the, that's what we have here, but which is P minus 1. Since UP is abelian, this is P minus 1, and it is given that Q divides P minus 1. So we have an abelian group whose order is divisible by f prime. So we can use the Cauchy's theorem for abelian groups to say that there is an element in UP of order Q. But because UP and this are isomorphic, this also would have an element of order Q. So we are going to write it directly. It follows from Cauchy's theorem for abelian groups that there exists an element T in the automorphism group of the cyclic group such that the order of T is Q. So that means we have found an automorphism of the cyclic group of order P such that the automorphism has order Q. There is something else also. Since G is abelian and P is different from the identity, T is not an inner automorphism of C. Oh, what have I written here? Since C is abelian, okay, where is G coming from? But what does this T not being an inner automorphism have to do with C being abelian? You think of inner automorphisms, you recall what they were. Say you have a group G and there is an element G in G. The inner automorphism corresponding to G or given by G is defined to be this map, which maps every element X onto G inverse XG. Now if your group is abelian, this would be what? G inverse Gx, that is equal to X. So every inner automorphism in an abelian group is the identity automorphism, which does not change any element. Now because our T is not an identity automorphism, it cannot possibly be an inner automorphism of C. And why is this not equal to identity? That is because its own order is Q, which is a prime, and hence it cannot be equal to 1. The identity automorphism has order 1. Inner automorphism of C. Do you now see that we have a we have a situation where we can talk about a non-abelian group of order PQ. We have a group C whose order is P, and we have an automorphism of C whose own order is Q, and the automorphism additionally is not an inner automorphism. So that means hence by the discuss exercise of section of the previous section, I think 8, no? Yeah, 2.8, this group about which we said many things when we were studying it, is a non-abelian group of order PQ. So that's how we have been able to produce or at least show that there exists a non-abelian group of order PQ if Q divides P minus 1. Now this fourth one is something for which we have to, I had to look outside and among the, my aim when I was myself trying to solve this problem, my aim was to take for the fourth one. In the fourth one, what do we have to do? We have to show that if we take a general non-abelian group of order PQ where P and Q are like this, then that is isomorphic to any other such non-abelian group of order PQ. I naturally tried to show that that group is isomorphic to this one, because this is my example of a non-abelian group of order PQ, and it has come out, I mean its existence has come out nicely using only the tools that we have seen so far. You see, this part C is not like part A and B where we had to use advanced results. So I was hopeful that I would be able to find some automorphism, some isomorphism from our general group of order PQ onto this group, but I failed actually. But Keith Conrad's notes contain one group with which you can show that there is an isomorphism with a general group of order PQ. So this part 4, it is coming from there, from Conrad's notes actually. Those notes are available online. Okay, so let us start. Let G be a, to emphasize the arbitrary nature, let us write any. Let G be any non-abelian group of order PQ. The beginning is the same. We again have those subgroups H and K. Let H and K be normal subgroups Wait, just hold on. Have I missed something in showing these things? Have I missed something? I mean, in part B particularly. Let me just see. I mean, in part B, I haven't written these things, no? I mean, we have already seen these things in the previous exercise. I haven't written these things in part B for our H and K, and still the solution went through. You check, okay, if you find any gap, please let me know. Whether we have to write these things or there is no need to write these things in part B. Please let me know. Let H and K be normal subgroups of orders P and Q respectively. So again, just like before, H and K will have generators. They will be cyclic groups. For some H and K belonging to G. Okay, and normality of H and K, of course, it is coming, first of all, existence of H and K is coming from part A. Normality of H and K, that is coming from part B. Since H is normal, hold on, which one have I taken here? H and K, these subgroups as in part B. N and H. Oh, okay, so N and H, that means N is the subgroup of order P. Here in place of N we have taken H. Okay, so that means what should we write? Since H is normal, there exists there exists a unique integer such that K inverse is equal to h to the power t. Because h is normal, if we form this element K inverse, because small h is coming from capital H, which is normal, this element would again be capital H, but because capital H is the cyclic group generated by small h, so this element would be a power of small h, and this capital H is a cyclic group of order what, n? No, what n? It is of order p, so this will be p minus 1. So because of that order, there would be a unique integer t lying between 1 and p minus 1, such that this would be equal to h to the power t. Do you see why t cannot be 0? If t is 0, then this right hand side is the identity. So cancelling k and k inverse from both sides, you would then get h equal to identity, which would contradict the fact that h cannot be identity because it generates a subgroup of order p, and p is not equal to 1. So that is why t is positive. Using this, one can prove that k to the power alpha times h times k to the power minus alpha is equal to h to the power t to the power alpha for all positive integers alpha. It's very easy, you just have to apply induction, that's it, induction on alpha. For example, if your alpha is 1, then this equation reduces to this equation. Here you have k to the power 1, which is 1, this is k inverse, and this one is h to the power t. In particular, if one takes q in place of alpha, q is a positive integer, then we get this h to the power t to the power q. We are writing this side first, that is equal to k to the power q h k to the power minus q. Since k has order q, so these two things become identity and you get h. Okay, so now note that this final equation h to the power t to the power q equal to h gives you what? Thus h to the power t to the power q minus 1 is equal to identity, and this calculation is in the cyclic group H, whose order is what? P, which implies that this is divisible by P, or this is congruent to 0 mod P, or t to the power q is congruent to 1 mod p. This relation we will use. And there is something else also. For any integer L, we have okay, which one? We are going to take this one. K to the power alpha h to the power L, k to the power minus alpha is equal to the justification for this step we have already seen, and I think in one of the exercises we in fact proved it. Either we made an exercise on our own to prove this, or in the solution to some exercise we proved that no matter what integer we have here, if you have a product like this which is called conjugate, I mean you multiply an element by another element on this side and its inverse from that side, such a conjugate behaves like this. Okay, this L comes outside and goes over all the things. Anyway, so now this becomes what? This is equal to this h to the power t to the power alpha whole to the power L. Keep in mind that we are saying L is any integer, L can be negative also. This is equal to h to the power L times t to the power alpha, or if you bring k to the power minus alpha on this side, you will get k to the power alpha h to the power L is equal to h to the power L times t to the power alpha times k to the power alpha. This also we are going to use. Okay, so all these things that we have done are with the abstract group G of, which is a non-abelian group of order PQ, nothing concrete. But now we are going to take a concrete non-abelian, fixed non-abelian group of order PQ, and then we will establish an isomorphism between this abstract group and that concrete group, proving that there is up to isomorphism only one group of order PQ which is non-abelian. So that is our next job, and this is where Keith Conrad comes in. And the type of group that we are now going to consider, that its elements are going to be matrices. Now consider, if you somehow are able to show that there is a general isomorphism, onto isomorphism between this abstract group of order PQ and our group of order PQ, that thing, then we won't need Keith's solution. I haven't been able to do that, but that does not mean you also won't be able to do that. Please try it. Maybe there is something obvious I am missing. Now consider, okay, let me write it here like this. These notations all are, I think, by him. Oh, and these matrices are coming from this, and there is an additional condition . Okay, so GP comma Q is this somewhat complicated looking set of matrices. Let us try to make sense of this first. What is JP? We already know what JP is. JP is the ring whose elements are these congruence classes modulo P under addition modulo P as addition and multiplication modulo P as multiplication, and we already know that because P is a prime, this ring is a field. JP2, according to the standard notation of sets of matrices, denotes the set of those matrices which are 2 by 2 matrices, 2 rows, 2 columns, and where the entries are coming from JP. That's just it. So this part of the set tells you that this, of course, is a 2 by 2 matrix, but these entries, these individual entries are coming from the field JP, and this equation should be true. So that means, you see, all these congruence classes, it's because these are congruence classes, so by the notation we are using in this book, we are enclosing the representative integers within square brackets. So these are all congruence classes modulo the prime P, right? Now the first observation is that this is a group, which is not very difficult. In fact, I will leave it to you. One can easily show that this is a group under matrix multiplication. For which what are the things that you have to do? You take any two such matrices, multiply them out, show that the result is again, first of all the result automatically would be in this set, the set of 2 by 2 matrices over the field Jp, but additionally this equation should also be true, which will become trivial. Okay, so that means this set is closed with respect to matrix multiplication. Associativity is true for matrix multiplication in general. The multiplicative identity where you have 0 in place of y and 1 in place of x, clearly you can see belongs to this set, and then like that you show that inverses also exist. So that will tell you that this is a group under matrix multiplication. And for these notations, in fact I should have written it here itself, but anyway, for these things, C section 1, 3 and section 6, 3. In section 6.3 there are matrices where you will get this notation, and in section 1.3 which treats the integers, we have these congruence classes and the things about them which we have already seen. Okay, the congruence t to the power q congruent to 1 mod p, which we have shown here, is equivalent to this equation. In the field Jp. Very easy to see. You already know this thing. This is equivalent to this. Note that we will need a little bit of number theory here, and we are going to borrow a result from Barton's elementary number theory. But because we are anyway going to prove those things one day, so we can use this. All of these solutions, those particularly which look quite long and somewhat complicated, may have surprisingly easy versions also, much easier versions. I would like to see such things. Note that t square, etc., t to the power q minus 1 are distinct solutions to this equation in Jp. Why are we so concerned about this equation? That is because this equation is a condition in this set. We are only considering those type of matrices where the first row, first column entry is a solution to this equation. Now, these are all distinct solutions to this equation in JP, which you can easily prove their distinctness. But here is the result. Theorem 8.5. Burton means Theorem 8.5 of Elementary Number Theory by David M. Burton. This type of reference means that makes sure that these are the only solutions. So that means in JP there are q minus 1, no, not q minus 1, starting from here we have q minus 1 and along with this one we have q. So there are q choices for the first entry. So we write accordingly. Hence, there are q choices for this combined with the p choices for y. We have the order of GP, Q is equal to PQ. You see, in these matrices, these entries are of course fixed. In the second row, we cannot do anything. In the first row, there are two entries and their choices are independent of each other. They are not no one of them is influencing the choice of the other. This can be chosen in Q ways. This can be chosen in P ways simply because it is coming from JP and there is no restriction on this. On this there is a restriction and that allows us to take only Q. It leaves us only with Q possibilities. This however has P possibilities and this in fact can be 0 also. This however cannot be 0. Do you see that? This congruence class cannot be 0 for obvious reasons. So that is why the total number of matrices that can be formed maintaining all these things is PQ, and that is also the order of this group. Now, since t is not equal to 1, t is not equal to 1, that's how we have chosen t in the beginning itself, okay. Oh, t is not equal to 1, I am saying that's how we have chosen t. Is that really the case? Have we really been careful in choosing t so that it is not 1? Let me just see one thing, okay. Oh, okay. We forgot to write one part. That's why there is a confusion. We cannot just simply write t is not equal to 1. This we should have done way before writing these things. Anyway, let us just write it now. If t is equal to 1, then you recall how we got t. I mean, what is t? Hn H inverse. No, that's not what we wrote. No. K inverse. Yes. K inverse is, according to us, h to the power t. So because t is 1, we would have this, or kh equal to hk. Now k and h commute with each other, and k is the generator of the subgroup K, H is the generator of the subgroup H, and just like before, their product is the entire group G. So just like before, this tells us that G is abelian. This implies G is abelian, a contradiction. So t cannot be 1. T is not equal to 1. And because t has been chosen in this way, and because t is positive and less than p minus 1, so t is also not just not equal to 1, but it is not congruent to 1 modulo p. In this, under this condition that t is different from 1, if you suppose that t is congruent to 1 modulo p, then you get the conclusion that p of course divides t minus 1, but because of those inequalities, t minus 1 itself is a positive integer less than p, and such an integer is not divisible by p. So combining this one and these inequalities, we have t is not congruent to 1 mod p, or writing the same thing in the field Jp, this congruence class is not equal to the congruence class modulo p containing 1. Now this non-equality would help us prove that the group we have created is in fact non-abelian. We thus have a matrix calculation like this. Let me try to write it as neatly as I can. Okay, if one calculates this product, this times this plus, so this is t plus 0, t plus 1, These additions are not ordinary additions, you should keep that in mind. This is addition modulo p, and these multiplications we have been carrying out, they are multiplication modulo p. 0 plus 0, 0, 0 plus 1, 1, and this matrix is not equal to this matrix. T 2t 0 1, which one obtains by multiplying again these two things but in the opposite order. T plus 0 t, t plus t 2t, 0 plus 0 0, 0 plus 1 1. This cannot be equal to this, because for that to happen the congruence class t should be equal to the congruence class 1, which is not the case. So that is why we have this thing. So that means the group we have constructed has order PQ and is non-abelian. Now we will define a map between this group and our abstract group. But before doing that, let us write our group GP, Q in a more revealing form. Now I need ink. Because we have seen that the first row, first column entries of any matrix in our group is one of those Q possibilities, so we can rewrite the group in this way. Thus, no matter this capital J, you recall, denotes the set of integers in this book. No matter what these integers m and y are, these will give us all the matrices. Of course, we need not have taken such general m, but it does not hurt to do so. Also, everything that we need here can be obtained by taking a suitable y. Now define phi from GP, Q to G by this formula. This matrix will be mapped by phi onto h to the power y times k to the power m. Recall that h is the generator of that subgroup H, k is the generator of that subgroup capital K. So whatever this element is, it is after all again in G, and y and m are integers, so these integral powers and their product, they make sense. But we have to prove that this is a well-defined mapping. That's the first thing we have to do. If you have two different representations of a single matrix, then those representations should not affect the final answer. You should get the same thing. So don't change the t here, t is fixed. You can change the m and y here. And another such m2 y2 0 1 such that they are equal. The notation is cumbersome, I admit, but it's better to write cumbersome notation and be correct than writing a slightly more convenient and shorter notation but be incorrect and create confusion. Such that these two things are equal. Then corresponding entries should be equal. Which imply what? These equations are equations in the field JP. So in that field, this will give you what? Okay, how are we able to divide both sides by this congruence class to the power m2, if you ask me? That is because this congruence class is non-zero. Why is it non-zero? That is because our t is lying in between 1 and p minus 1. This congruence class being 0, forget this m2, only this congruence class being 0 is equivalent to p dividing t. That is not possible with these inequalities. That's why it's non-zero. So it's a non-zero element in the field JP, so its inverse exists, and in fact any such power itself is a non-zero field element. That's why we can write an equation like this, which comes from here. And now you have this. So what does it tell us? It tells us that Q divides M1 minus M2. Why? Because you see, we have already seen one thing, no? That this equation has so and so solutions, right? Now if you divide this thing by Q, divide this thing by Q means using the division algorithm, you will get a quotient and a remainder. Now in that quotient and remainder, the quotient part, let me just show that what I am trying to say here. Suppose this is equal to some beta times Q plus a remainder rho. Now if you raise this congruence class to this power, then on one side you will have 1, on the other side you will have this, no? So from there, what are you getting? That this is equal to 1, where rho is, because it is the remainder when you are dividing something by Q, rho is less than Q. Now if rho is non-zero, then the fact that those solutions to this equation in JP are the only solutions that will be violated, because if this becomes equal to 1 for a smaller value than Q, for a smaller exponent than Q, and at the same time that thing is also positive, then we won't even reach this power. Before that itself we will things will stop, and then it will start getting repeated. So that thing is violated. So that is why Q divides this. But Q divides this means M1 is congruent to M2 modulo Q. So that's what we are going to write. Or instead of, okay, oh, why did I have to say so much? I can argue in a slightly different manner also, no? This is an equation in JP, fine. There is no need to consider all those things. This is not just an equation in JP, but this is an equation in this non-zero system. That is what I mean by that is the system obtained after removing the zero, and we know that since JP is a field, this is a group under multiplication. In that group this is an equation, and the okay, will it give me the thing that I am seeking? Now I don't think it will give me the thing, because JP has how many elements? Okay, let's just forget that. We have already argued like that, and we have seen that Q divides M1 minus M2. Which imply M1 is congruent to M2 mod Q, and from this one directly we get Y1 is congruent to Y2 mod P. These congruences give us m1 y1 0 1 5 equal to h to the power y1 k to the power m1, that is equal to, let me write it there, this is equal to h to the power y2 k to the power m2. These congruences imply that h to the power y1 is equal to h to the power y2. Why? That is because you see y1 is p times something plus y2. So that p times, so if you write that exponent here like that, p times something plus y2. Now have I written that thing differently? Wait, I may have k to the power m1. Now it's okay. So what was the order of, yeah, it's okay, there is no problem. The order of h is p, so if you write y1 as p times something plus y2, that is equal to h to the power y2. Similarly, the order of k is q, so because of this congruence we have k to the power m1 equal to k to the power m2, and this is nothing but the phi image of this other matrix. So if the inputs are equal, the outputs are equal. Hence, phi is well defined. Also, phi is evidently onto. That you can see from the definition of phi itself. Oh, by the way, why? You take phi is a map from G p comma q to G. So if you take any element of the second set, the codomain, then it can be written as a product of an element of capital H and an element of capital K, because capital G is capital H capital K. Now because capital H is a cyclic group which is generated by small h, so it will be of this form, and in any general element of capital H times any general element of capital K, and this comes from such a matrix, you know, but t to the power beta plus h to the power congruence plus alpha 0 1. So that is why phi is evidently onto. Okay, now comes the crucial thing for which we had to do so much, that this phi is actually a homomorphism. Now for t to the power alpha beta 0 1 comma t to the power gamma delta 0 1 in gp comma q we have so we will multiply these two matrices and on their product we will apply phi. Alpha plus gamma. T to the power alpha delta plus beta 0 1. On this we apply phi. So according to the definition of phi, which I always forget, what was it and which one goes where? This one comes afterwards, this one comes first. Okay, and this is h. Okay, so this is equal to h to the power t to the power alpha times delta plus beta, k to the power alpha plus gamma. Okay. Now what we do? Now we use the rules of exponents in the original group G and write this entire thing as h to the power beta, h to the power delta times t to the power alpha times k to the power alpha times k to the power gamma. And this one, if you go back to that L identity, is we had something like this now. K to the power, I mean, if you go to the L identity, what I have written here, I have changed all the letters. So right now I can't figure out what I wrote there. The thing is just this: k to the power alpha, h to the power beta, or rather h to the power L is equal to h to the power L times t to the power alpha and then after that k to the power alpha. This thing. So we now have the right hand side, but in place of L we have delta. So that means we can in its place write this thing also. The order will get changed. K to the power alpha stays as such, and we have h to the power delta, k to the power gamma. So you can see then again using associative law and all those things, we can write, keep in mind this calculation, after application of phi, this calculation is happening in our abstract group capital G. Gamma, and this, if you look carefully, is your phi image of this. This is equal to this, alpha goes here, beta goes there, and this one is gamma goes here, delta goes there. So that is why this strange mapping phi is actually a homomorphism, and that too an onto homomorphism. Now the only thing left for us to show is that phi is 1 to 1. We managed to show that, then we are done. For that, what we would do, we would consider an element in the kernel of phi and show that that element must be the identity element of the domain. Hence, let us write the conclusion. Phi is a homomorphism. Okay. Next, let this belong to the kernel of phi. Then kernel of phi means it should be the identity. Identity is equal to the phi image of this matrix which by the definition of phi is h comes first and then k, h to the power y, k to the power m. Since h and k are intersecting trivially, and from this equation you get h to the power minus y equal to k to the power m. Note that this element, because it's the power of h, belongs to capital H. Also, because it's the power of k, belongs to capital K. So both of them must be equal to the identity. We thus have hence, because the order of h is p, so p divides y, and the order of k is q, q divides m. So this element in the kernel, we already know that the qth power of this congruence class T is the congruence class 1. Because m is a multiple of q, so we will have a q factor here, so that means this power will be equal to 1. And because p divides y, this congruence class becomes the zero congruence class. And this is nothing but the identity element in our matrix group. This shows that K phi is the identity. First, you should understand that this notation is the general one. This E right here is this matrix, and hence phi is 1 to 1. Phi is thus a 1 to 1 homomorphism of Gp comma q onto G. So G and Gp comma q are isomorphic, and because G is arbitrary, so any non-abelian group of order PQ is isomorphic to this specific group Gp comma q, and so all of them are isomorphic among themselves. So up to isomorphism there is only one non-abelian group. But what I feel about this solution is that if one carefully looks at the solution and sees the relationship between these matrices and the corresponding entry in our abstract group G through which we have set up the mapping, one can I think do a similar thing with our other non-abelian group C comma T of order PQ. I mean, you just have to, looking at these matrices, you have to identify what the corresponding elements in this are. If you can do that, then we won't need to construct this extra group. But the solution we now have, okay, that much is there. So I end the video here itself. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. And tomorrow we have Gallian's exercises, 2 videos, one on groups and one on rings. And on Sunday we of course have our analysis, where we will address that thing which we where we left off. We in fact got stuck with that L sigma identity, but it can be, I mean, things can be nicely salvaged. I have already seen, so we will do that. So anyway, see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.